deal with sequence, okay, RNN obviously is a common choice, but when the sequence gets long, okay, CNN actually is also a good choice, okay, as I will show you later in this chapter, okay. So this is the first scenario. The batter hit the ball, okay, the outfielder, okay, so immediately starts running, okay, so he's going to anticipate, okay, the ball's trajectory, okay, so I mean, he's going to track it and and change his speed, okay, accordingly, and then able to catch the ball, okay. So I think a lot of us is able to do that, but of course we are not professional baseball player, but predicting the future, okay, is something we do all the time, okay. Of course, I'm not saying like a long-term prediction or like the prediction here I'm talking about is probably I should use another word like anticipation, okay, anticipation, okay. So, for example, when you are finishing your friend's sentence, when you have a very close friend, when he or she is talking about something, okay, you are able to finish his or her sentences. This happens a lot of time, right? Or okay, this is all. This is also happen very commonly. Okay, anticipating the smell of coffee at breakfast. This one, okay, perhaps like this is a good example for Western people, okay, because Western people like drink coffee every morning, okay. I do know like a lot of us like drink coffee in the morning as well, okay. So you may experience something like that, but let me use another example which is much more common for for us, okay. For example, like when you see a picture of plum, you start have like a mouth water running, right? 望梅止渴. Okay, when you see a picture of a plum, then you feel like you have mouth water. Okay, it's this is like very common. Okay, why is that? Why is that? I mean, so this is the kind of like anticipation, because when your brain, okay, feel like it is something's going to happen, it tells your body to react in advance, because plum is sour, right? So you need more mouth water to go with that, So anyway, just want you guys to understand, okay? The prediction that I'm talking about is not necessarily like, okay, you are able to predict like, stock price is going to go up or go down, okay? Or like, okay, there's like a earthquake, like, we had earthquake last night, right? I mean, I'm not sure if maybe some of you didn't feel it, because it's for people in Taoyuan it's not really a large earthquake anyway. But yeah, I mean, it's still now like it's very difficult to predict the earthquake. We know that, right? So basically, okay. So the prediction here, I'm talking about. Here is not about those like a big thing. I'm talking about like a little small thing, and a much shorter period of time prediction. Okay, so maybe not using the prediction, but using like anticipation is probably a better word here. But you get the idea. Okay, so we do that all the time. So in this chapter we'll discuss recurrent neural network. Okay, so this is a class of the network that can predict the future, okay, at least up to a certain point, okay, and they can analyze time series data, okay, including stock price, tell you when to buy or sell, okay. Actually, my student, the student in my lab did like research, like this type of research, and at least according to analysis, I mean simulations, we are able to make big money using the system, but well, I never use it. Because I'm not a big fan of the stock, but yeah, because those two students who did that topic, they actually work for like an investment company, okay? So I'm not sure like if they are going to use those system in their company or not. That one I'm not sure, okay? But anyway, okay, so in autonomous driving system, okay, this type of, they can anticipate the car trajectories and help avoid accident. This is one of the active research project in my lab, okay? We are still doing that, okay? Of course, like, it is not necessary like just RNN nowadays, okay? If you want to, get a better result of that, okay? It is actually one of the toughest like problem, okay? More generally, they can work on sequences of arbitrary length, okay, rather than on fixed size inputs, okay? So all the network that we have considered, okay, so far, expect fixed size of the input, okay? Unless you are talking about fully convolutional network, okay? Yeah, for different size of input, the fully convolutional network is able to deal with that, but not as convenient, not as like powerful as like RNN, as you will see later, okay? So for example, they can take sentences, documents, or audio samples as input, making them extremely useful for natural language processing application, okay? Such as automatic translation or speech to text, okay? But for that, okay, RNN could be used for NLP application, but it is actually covered in a different chapter. As I said, I'm not going to cover that chapter, but once you learn the material in this chapter, you are more than welcome to check out that chapter by yourself, or you can take Professor Cai Zhonghan's class, okay? He has an NLP class, I think this semester, right? Okay. So he offers this class every year. What's going on? Okay. So, to be exact, okay, what we are going to talk about, okay, in this chapter, we will first look at the fundamental concepts, okay, for RNN and how to train RNN using backpropagation through time, okay. You guys know backpropagation already, but what is backpropagation through time? Okay, this is a new thing, okay. Then we will use the RNN to forecast time series. Okay, I will show you an example of that. Okay, after that, we will explore some difficulties. Okay, that you will encounter when designing RNN. The first one is unstable gradients. Okay, we talked about unstable gradients previously already. Okay, but okay, RNN has its own unstable gradient problem, okay? Because like the previous approach, okay, that we covered in chapter 11, okay, for example, such as dropout or like batch normalization, unfortunately, do not work well for RNN. Okay, so we will have to talk about recurrent dropout and the recurrent layer normalization, Okay, they are sort of replacements of those things. Okay, but they of course are, only work for the RNN network. Okay, and also okay, RNN sometimes have this short-term memory problem. This is especially the case when your sequence is long. Okay, how to fix that? Okay, there are different type of neurons you could use. Okay, to alleviate this problem. I'm not saying you can completely get rid of this problem, but at a large degree, okay, alleviate this problem. Okay, two of the most famous recurrent neurons are LSTM and the GRU. Okay, so we are going to talk about all this in this chapter. We are also going to, talk about how to use CNN to handle the sequential data. Okay, for small sequences, okay, RNN can get the job done very well, but for very, very long sequence, for example, like such as audio sequence, okay, then actually CNN actually works better. Okay, so there's a particular type of CNN that is like proposed by what's that company's name? The company that designed AlphaGo. What's the name of the company? DeepMind, yeah. So this WaveNet, okay, is used to deal with particularly long sequence data. Okay, they designed this one as well. So the DeepMind is not. They actually made a lot of contributions to deep learning. Okay, not only AlphaGo, but also WaveNet, and unfortunately we will not have time to talk about that. But they actually, AlphaGo actually use a lot of like reinforcement learning, and they pretty much revolutionized the reinforcement learning. Okay, this company. So this company is actually like has a lot of like very important contribution to deep learning. But unfortunately we don't have time to talk about reinforcement learning this semester. Okay, so in chapter 16 we will continue to explore RNN and see how to use them for NLP. Okay, along with more recent architecture based on attention mechanism. But as I say, chapter 16, we will not cover chapter 16, unfortunately. Okay, I leave this sentence here is just because like sometimes when this class, when the deep learning class happen to become like 2 semesters, then I will have time to talk about that. Yeah. So anyway, okay, so up to now, okay, all the neural network we have seen, okay, are pretty much feed-forward neural networks. Okay, this include MLP as well as the CNN. They are pretty much feed-forward neural network. Okay, the activation flow only in one direction. It goes from the the input layer all the way to the output layer. Okay, so there are some exceptions, okay, in Appendix E, but we didn't talk about Appendix E anyway, so you don't need to worry about that, okay? So a recurrent neural network, okay, it's going to be, very different, okay? It looks like a feed-forward neural network, except it also has a connection pointing backward. So it has a connection that points back to itself. So it's kind of like a feedback mechanism. Okay, feedback mechanism. Okay, so let's look at the simplest possible RNN composed of only one recurrent neuron. Okay, it receives input, produce output, and sending the same output back to itself. So this one. So you can see this is a recurrent neuron. X is the input, and it do some computation, and it will output y, but at the same time, it will, feed back the output y, okay, back to itself. So it is going to use x and this input, this feedback, both of this input and the feedback as the input of this neuron. So you may ask, like, how does it happen? This is actually happened in time step. Okay, time step. We call each of these as a frame. So this t minus 3, you can treat this t minus 3 as different time frame. Okay, so you can see at the time, for example, at the time t minus 3, okay, you have the input x t minus 3, and you get the feedback from the previous output, okay, and then you do the computation, and then you have this output yt minus 3, and this yt minus 3 will be feedback to the time step t minus 2, okay, to be the input of the same neuron, Okay, the reason we draw like this is like we try to expand in the time dimension. Okay, all this represent just this neuron. Okay, but if you do not expand, what happens with different time step? You probably do not understand. Okay, every time this feedback is not going to be used at the same time step. It is going to be used, okay, at the next time step. Okay, something like this. So you may wonder, well, how about at the very beginning? Okay, when this neural network start functioning, what happened? I mean, you obviously you don't have you don't have feedback from the previous time step because that's the first time step, right? So you will just consider this feedback input to be 0. Okay? So this is like what's going to happen. We call this expanding, like in the time dimension as unrolled through time. Okay? So if you see this, you get an idea that, okay, actually this neuron is capable of handling like an input of arbitrary size, right? Obviously, because, well, because we consider the time dimension. So, you just, if you have multiple input, you just feed that, input to this exact same neuron at a different time step, and it is able to take, as many, input like stuff as possible as you want. Okay, so that is why RNN is, is considered like it can take like arbitrary input size. Okay, so as for the output of the single recurrent neuron for single instance, okay, you can easily create a layer of recurrent neurons, right? So at each time step t, every neuron receives both the input vector xt and the output vector from the previous time step y t minus 1. So it's going to be something like this. This is a layer of recurrent neurons. So you can see it is going to it gets the input. This x is a vector. Okay, it gets the input vector x, and it will output a vector y, and this vector y, okay, in the previous time step will be feed back to the current time step as the input again. Okay, so if you can also do like unroll through time, okay, and get idea like this. Okay, so each recurrent neuron has two sets of weights, okay, one for the input xt and the other for the output of the previous time step yt minus 1. So we call this weights vector, okay, wx and wy. So if you write it into formula, okay, it's going to be something like that. Yt is the result of xt, okay, transpose times wx, okay. So this is like a weighted sum of the current input plus weighted sum of the feedback, okay, weighted sum of the feedback, okay, plus a bias, of course. And then after you add all this, you have to go through an activation function, okay. This activation function, okay, it could be ReRU, it could be hypertension. To be, by the way, hypertension is used very often in RNN network, okay, to a point that RNN treat the hypertension as a default activation function, okay. But of course, if you want, you can still use the ReRU, okay, if you want, okay. I just want to point out that the activation function, okay, in RNN is mostly ReRU, okay, a lot of time, okay. But obviously, ReRU has its own issue, as I have mentioned earlier, okay. But we know how to deal with that, right? So, so if you have like the whole set of like neurons, okay, then because it becomes a matrix, right? It becomes a matrix. So it's going to be something like this, okay, in the metric format. So in the metric format, you can even abbreviate it like this, where this W is of this format. Okay, if basically this one times this one is this one. This is obvious, right? Okay, so this is when you have a mini batch. Okay, if you only have a vector, then it's going to be it's represented like this. But if you have a whole batch, then it's a little bit more complicated. It's going to be a matrix format, and this basically talk about like the dimension of all of each of these metrics. But I think this are obvious. You can easily check it out. So yt is a function of xt and yt minus 1. And yt minus 1 is a function of xt minus 1 and yt minus 2. And yt minus 2 is a function of xt minus 2 and yt minus 3, and so on. So you can expand this all the way until what? Until time step 0, where x0, there's no y, negative 1. Okay, as I say, y negative 1 basically is a zero, just a zero vector. Okay, so you can see that once you expand this, okay, you will understand that yt is dependent not only to the current input, but also all the previous input. Okay, so x0, x1, x2 is up to xt. So yt is dependent to all these. Okay, so this is why, okay, we consider this neural network as a memory, okay, because it sort of have a way to make use of the input of the very beginning. Okay, so so it has some certain, you can consider it a certain type of memory. Okay, and many researchers prefer to use hyperbolic tangent, as I said. Okay, activation function rather than ReLU, but the ReLU based on are also possible. Okay, so since the output of recurrent neuron at time step t is a function of all the input from the previous time steps, so you could say it has a form of memory, as I said. Okay, a part of neural network that preserves some state across time steps is called a memory cell. Okay, so a single recurrent neuron, okay, is a very basic cell. Okay, later on, okay, in this chapter, we are going to talk about more complex and more powerful memory cell. Okay, which are actually LSTM and the GRU. Okay, this actually like this type of neuron. Okay, the complicated neuron architecture is still actively researched, I mean, even for now. Okay, so in general, cell state at time step t actually can be denoted as HT. This is a state of a neuron. Okay, H stands for the hidden. Okay, so because it's a hidden state. Okay, so this is a function of some input at that time step and its state at the previous time step. So its HT is going to be the function of HT minus 1 and XT. So you feel like, well, this looks just like a YT, right? Sort of, yes. Okay. Its output at the time step t denoted by YT is also a function of this. Okay, and the current input. Okay, so in case of the basic cell, as I have shown you, the HT and the YT are pretty much the same. Okay, the hidden state and the output are the same. But in a later discussion, when we talk about more complicated cell structure, okay, these two things may be different. So this is a more general situation. Okay, the input is X, the output is Y, and we have a hidden state H as a feedback. So it's going to be, when we unroll this through time, it's going to be something like that. Okay, and in a basic RNN cell, the Y and the H are the same, but it is not necessarily the case for more complicated cell types. Okay. So, an RNN can simultaneously take a sequence of input and produce a sequence of output. Okay. So here we are talking about 4 most commonly used RNN architectures. Okay, something like this. The first one is called sequence to sequence. The second type is called like sequence to vector. The third type is called vector to sequence. The fourth type is called encoder-decoder architecture. Okay, so here we are going to talk about these 4 types. Okay, and their common applications. Okay, for example, the sequence to sequence, okay, is normally used for predicting time series. For example, it can be used to predict stock prices. So you feed it the prices over last n days, okay, and it will output the price shifted by 1 day into the future. So from n-1 day to tomorrow. Okay, so this is like what's going to happen. Okay, so this sequence to sequence, okay, we are going to revisit this sequence to sequence architecture, okay, in the example, okay, in the example. So alternatively, okay, you could feed the network a sequence of input and ignore all output except for the last one. Okay, this is sequence to vector. Okay, sequence to vector. So you could feed the network a sequence of words, corresponding to a movie review, okay, sequence of words corresponding to a movie review is considered as a sequence, okay, and the network would output a sentiment score, okay, basically to represent like a, is this review positive or negative? Okay, positive means +1 means the review loves this movie. Reviewer loves this movie. -1 means the reviewer hates this movie. Okay, so this can be output by that single output. Okay, so this is the sequence to vector, and we can also have a vector to sequence. Vector to sequence. Okay, you can feed the network a single input at the first time step. Okay, and zeros for all other time steps, and let it output a sequence. Okay, so this is a vector to sequence network. Okay, for example, the input could be an image, and the output could be a caption for that image. The caption obviously is some description, right, of words. So I mean, description of words, I mean, is considered like a sequence. Okay. So last one. Okay, you could have a sequence to vector network. Okay, this sequence to vector network is called the encoder. This one. This one. This part we call it encoder. So this is pretty much a sequence to vector. Okay, and then you have a vector to sequence. We call that decoder. Okay, so this is like this structure is a lot of time used for language translation. Okay, so the input is a sequence, the output is also a sequence. So you may ask, well, so since the input and output are both sequences, why don't we just use the first type? Sorry. What's the difference between this one and this one? Okay. Let me first explain, okay, how the translation, happens. Okay, basically here, okay, obviously you feed like a word in a sentence. Okay, maybe in English. Okay, and that whole sentence will become an embedding. Remember, I explained the concept of embedding to you guys earlier, right? So it's kind of like a lower dimensional vector representing like the meaning of that sentence. Okay, so it passed that vector to this decoder, and this decoder will then translate like into another language. For example, maybe Chinese. Okay, something like that. Okay, so the difference between this one and that one is in the sense that, okay, because in a whole sentence, I mean, the last few words may have big impact to the meaning of the whole sentence, right? Right? For example, like in English, if I say, can I have some example? For example, like if I say, can I go to the movie? Probably not. Okay. Okay. For example, I say, shall we go to the movie? Let's go to the movie, right? Okay. If I add like a last word, okay, then I'm asking, right? I'm asking you, okay, we want to go to the movie or not, right? But without that right or okay, the last word, let's go to the movie. It's a passive sentence, right? It is not a question sentence, right? It's not asking, okay? So you can see this example, okay? The last few words may have a big impact to the to the meaning of the whole sentence. So in this situation, you are able to, consider all the input of every words in the sentence and put that into an embedding, and then be able to translate the sentence, okay, with the consideration of every single word in the sentence. But in here, okay, if you are doing like a shall we go to a movie, okay, then because this input, okay, is going to only impact this part. The previous part, there's no way this input is going to be fed to the previous recurrent neurons. So this input cannot be used to have any inference to the previous translations. In many language, okay, this may produce incorrect translations. Okay, so that's the issue. Okay, so that is why this architecture is more often used for language translation. Okay. So you guys know we have sequence to sequence, sequence to vector, vector to sequence, and encoder decoder architecture. That is, those four types are the most commonly RNN architecture. Okay, so how do we train an RNN? Okay, to train RNN, okay, we are going to unroll it through time. Okay, and then simply use a regular backpropagation. Okay, so this strategy is called backpropagation through time, BPTT. So it's going to be something like this. Okay, so this is like this is actually an RNN network. Okay, but with a weight and a bias. Okay, and because we unroll it through time, so you can see like we have all these. But sometimes we only consider, for example, the last few inputs. For example, Y2, Y3, and Y4. Okay, we have like the ground truth of this, and then we do the comparison, and then it's able to calculate the error. Okay, and those errors will be considered as a gradient that's flow back through this direction, and this arrow, this gradient flow back is also going to flow back to, through this unroll through time stuff. Okay, but these two, okay, these two outputs, they are not, okay, if they are not used in a cost function, then pretty much we don't consider them. Okay, there's no gradient flow back in here. Okay, so based on this, one thing you can learn, okay, is that, okay, when you train the RNN, okay, there are two considerations, because in the previous cases, when you train MLP or CNN, okay, most of the time, like the only matter is the layer, right? The more layer you have, or each layer, if you have more neurons, then how should I say? The training become more difficult. You may need more memory. You may take more time to train. But in an RNN, okay, the number of neurons in a layer as well as number of layers still matters. But one more factor to consider is how many, time steps do you need to consider, okay, when you do this unroll through time. during training. So the time step, okay, to expand is also one factor to consider. This add like one additional complexity when you train an RNN model. Okay? Just want you to be aware of that. Okay? So let's take a 10 minutes break. When we come back, we will continue the discussion. We are going to talk about an example of RNN network. Okay? Okay, so let's try to finish this class. Okay, last hour. Okay, so suppose you are studying the number of active users per hour on your website or daily temperature in your city. Okay, these two problems. Okay, active users per hour or daily temperature in your city. These two, you have only you pretty much have only one number per time step, right? Okay, I mean at each step you have a particular number of active users, or at each day, okay, you have a temperature in your city. Okay, so those two things are just you're trying to get a single number, okay? Or your company's financial health measured quarterly using multiple metrics. So this is a little bit more complicated, okay? Because you are measuring your company financial health, okay? And there are multiple metrics. So this means at each quarter you need to estimate like a set of numbers. Okay, so no matter in all these cases, the data will be a sequence of one or more values per time step. Okay, for the first two, each time step you have one value. For the last one, okay, each time step you have multiple values. Okay, so this is called a time series. Okay, so in the first two examples, there is a single value per time step. So these are called univariate time series. Okay, so this is what we call univariate time series. Okay, the last one, okay, the financial example, there are multiple values per time step. Okay, for example, the company revenue, debt, and other stuff. Okay, so it is a multivariate time series. Okay, so typical task is to predict future values. Okay, either the future active number of active users or future temperature, like the temperature for tomorrow maybe. Okay, or like the company financial health for the next quarter. Okay, so you are predicting this. Okay, this type of approach is called forecasting. Okay, another common task is to fill in the blanks. Okay, sometimes the data set has some empty, some missing values. Okay, those are blanks. Okay, to predict or post-dict the missing values from the past. Okay, so this is called imputation. Okay, imputation is to fill in the missing value, pretty much. Okay, so for example, the figure in next slide shows 3 univariate time series, each of them 50 time steps long. And the goal here is to forecast the value at the next time step, okay, which is represented by the x for each of them. So this, you can see, this is time series, and you have first 50 steps, and the last one, the one you want to predict is here. And this one, okay, you have first 50 values for the first 50 time steps, and last value you want to predict is here. The next value you want to predict, and this one is something like this. Next value you want to predict is here. Okay, So this is the thing that we want to deal with. We want to deal with time series forecasting. Okay. So, okay. For simplicity, we can use a time series generated by the generate time series function. Okay. So we create a generate time series function. So it is like this. This is a very simple function. Okay. So generate time series. The batch size and the number of steps are the arguments to pass to this function. Okay. So we have frequency 1, frequency 2, offsets 1, offsets 2. Okay. We randomly generate these 4 numbers. Okay. And time equal to this linear space. Okay. We prepare this. I mean, for each batch, for each batch, we have a number of steps. Get them ready, and then okay, you can see series equal to 0.5 times. This is sine, right? I mean, you guys should be familiar with that triangle. Those sine, cosine, those stuff. Okay, so this is non-pi sine. Okay, time minus offset 1 times the frequency times 10 plus 10. Okay, this is wave. This represents wave 1. Okay, so we first add this to the series, and then we add another wave. Okay, which is defined by this one, 0.2 times sine of this thing. Okay, so this is a sum of 2 waves, and then we also add a noise here. We add another noise. Okay, and then we return this series. Okay, so this is the microphone is dead. Okay, anyway, so we are going to we basically here we use these 2 waves. We add up these 2 waves and add some noise. Okay, and use this as our time series. Okay, so this function creates as many time series as requested. Okay, so how many time series? Okay, defined by the batch size argument. Okay, so each of length n steps. Again, this n step is defined by the argument. Okay, and there is just 1 value per time step in each series. Basically, it's controlled by this. Okay, so all series are univariate. Okay, the function returns a non-pi array of shape, batch size, time steps 1. Okay, the reason this is 1 is because it's univariate. Okay, so where each series is the sum of 2 sine waves of fixed amplitude and but random frequencies and phases. Okay, plus a bit of noise. Okay, so something like this. Very simple. This is very simple data that we create. Okay, we want to use it. I mean, as an example to showcase how we can predict this. We can deal with this prediction. Okay, because if you want to do the prediction, you need to know the ground truth, right? So here, okay, see the n step is 50. Okay, the series is generate equal to generate time series. Okay, 10,000 n steps plus 1. Okay, this is so we have 10,000 series. Okay, because we have each batch has 10,000 series. Okay, we have only this batch. Okay, 10,000, and each series is 50 plus 1. Why is it plus 1? Because we want to predict the next one. Okay, so actually each series will have to generate 51 value. Okay, and then we will break this series into training set, validation set, and test set. Okay, so I think this is very easy to explain. So I will not go into a detail here. Okay, so we have training set, validation set, and test set ready. Okay, the first 7,000 series are used for the training set. The 7,000 to 9,000, these 2,000 series are used as a validation set, and the last 1,000 is used for the test set, okay? And then, okay, so before we, design our RNN model, okay, we want to, have some baseline model to compare with. Otherwise, you don't know how good or how bad your RNN model performs, right? So, yeah. So there's like a simplest approach to predict the last value in each series, okay? This is called naive forecasting, okay? This is provided actually by Python. Okay, Python actually has like a default naive forecasting function that you could sort of use. Okay, so it's sometimes surprisingly difficult to outperform. Okay, in this case, okay, you try to use, okay, I mean, y predict equal to this x valid, okay, -1, okay, I mean, it will automatically fill the last value for you, and then you try to compare this prediction with the real, with the generated value, okay, that we know, the ground truth that we know. So you calculate the mean square error, and the mean square error is 0.020, 211, blah, blah, blah. Okay, you get the idea. So this is actually pretty good, right? Pretty good, okay, 0.02. I mean, quite low, right? And then, okay, another easy approach that we can use for we can use as a comparison is like we can use a fully connected network. Okay, a very simple fully connected network like this. Keras models, sequential. Okay, in this model, we first have a flattened layer of shape 50. Okay, 1. And then, okay, because we want to output the prediction, right? So we just output a dense, the output layer is only 1 neuron. Okay, so be very careful here, okay? In this, we could say this is a multi-layer perceptron, but really, it does not have any hidden layer, right? This is input layer, this is output layer, and we don't have any hidden layer in between, right? So to be honest, this is more like a perceptron. Okay, this is more like a perceptron. Okay, so we can refer this one. Okay, you know perceptron. I mean, we talk about perceptron like at the beginning of this semester, right? I told you guys perceptron is a linear model, right? Okay, yeah, I mean, we have 50 neurons. And this 50 neuron will connect to this dense layer, with 50 connections. So each connection has a weight, okay? And we also have bias. So yeah, you can use the MSE loss as a default, and then you train this for 20 epochs, and using Adam, using Adam optimizer, and the MSE, okay, if you use the validation set, MSE is like 0.004. It's pretty good, right? Pretty good. It's better than the naive forecast. Okay, naive forecast. Naive forecast is 0.02. This one is 0.004, which is 5 times better than the naive forecasting, right? Okay, so we want to see if we are able to, if we use RNN, can we outperform this, these two baseline? Okay, so the first one is a very simple. Okay, so we just create a simple RNN with 1 neuron. Okay, so input shape is none, 1. None means it accepts any size of the input. Okay, and each input size is 1. Okay, because it's univariate. Okay, And then, okay, if you do not set the, we do not need to specify the length of the input sequence, okay? Since a recurrent neural network can process any number of time steps, okay? So, so we can, train this model, okay? Oh, by the way, by default, okay, you don't see like an activation function here, but the simple RNN layer by default use hypertension, okay? By default use hypertension, okay? So yeah, it's just like the easiest like a simple RNN that which the h is equal to y, by the way, okay. And the first and initially like the previous feedback is 0, okay, just like what we described earlier, okay. So it's going to take the x0, x1, x2 up to x49. And it is not going, all the output will be ignored until the last one, y49. It's going to be used to compare with like the ground truth. So so you can imagine. Okay. So in this model, actually, we have to expand this to 50 time steps. And the last one will be used to compare with the ground truth, right? Which will flow back, okay? The arrow will become flat gradient to flow back to do the certain modification to the weights, okay? And during the training, okay? So, yeah. And also, okay, the recurrent layer in Keras only return the final output, okay, by default. So to make them return one input per time step, okay, in other words, like to output sequence, okay, if you get a sequence, you want it to output sequence, then you have to set return sequence equal to true. Okay. I mean, you will see this later on. Okay. So if you compile, fit, evaluate this model, okay, train for like 20 epoch using LM, and the MSE will reach 0.014. So, well, it's better than the naive approach, right? But it's not as good as the simple linear model. This simple linear model is referring to that fully connected, well, you can say it's MLP, well, but actually it is pretty much just a perceptual model, okay? So why is that? Because that perceptual model, okay, as I said, okay, we have 50 connections, including one bias. Totally, we have 51. We have 51 weights, right? 51 parameters. But for this simple RNN, we have only one neuron, right? For that one neuron, how many parameters do we have? We have one weight because it's a univariate, right? We have one weight for this input. We have one weight for this one, and one additional weight for the bias. So totally, for that simple RNN, we only have 3 parameters. Okay, to train. Okay, to tune, basically. So yeah, from the information theory point of view, this is really this model is really too simple, okay? Too simple to get a good result, okay? I mean, think about this, okay? With just 3 parameters, okay, it already reached like 0.014. It's not too bad actually. It's not really that bad. Okay. Compared, with like the linear model which has 51 parameter, and yeah, that one outperformed this, but really like in terms of if you compare the number of parameters, really like that's understandable. Okay, so our simple RNN was too simple to get good performance. So let's try to add more recurrent layers. Okay, so the first thing, okay, we could add is that we can add more layers. Okay, if you want, we can add more neurons per layer as well. Okay, but if you remember, like just like any other neural networks, okay, adding for the same number of parameters, a network with more layer is more powerful than a network with more neuron per layer. Okay, so yeah, even though we can add more neurons per layer in this case, it's probably a better idea to just add more layer. Okay, so there are many other models to forecast time series, such as weighted moving average model or autoregressive integrated moving average. This is abbreviated as ARIMA. I'm not sure if your background is from mathematics or statistics. This word ARIMA should ring a bell to you. Okay, this is like one famous model that is used to predict the time series data. Okay, but some of you, okay, some of them require you to first remove the trend and the seasonality. What is trend and seasonality? Okay, for example, if you're studying a number of active users on your website, and we know from a prior knowledge that this number of active user actually growing by 10% every month. So you could, what you can do is that you can remove this trend from the time series. Okay, you can, for the training data, because it must be, from many previous months, right? So you can remove like that 10% extra active users from all the data training data set, and then use that to do the training. Okay, and then after you get the prediction, you can add that trend back to get the final prediction. Okay, this will usually make the prediction better. Okay, this usually will make prediction better. So this is for the trend, right? Another one is seasonality. What is seasonality? For example, if you want to predict, trying to predict the amount of sunscreen lotion sold every month. Okay, well, we know sunscreen lotion is probably used for people who go swimming, right? Okay, if you go to beach, then to avoid sunburn, you use sunscreen, right? So obviously, this type of goods sell better in the summertime, right? Okay, and it doesn't sell that well in the winter time, right? We know that, right? We know that. So if you try to see okay, it's the amount of sunscreen lotion sold every month, then you will see sort of like a peak during the summer, and for the other season, especially winter season, you will see pretty much not too many people buy sunscreen. Well, for some people, in US, there are some female who likes to get like a certain sunburn, okay, there's like a sunburn machine. You can lie down in that machine to get like a tan, okay. I mean, to make your skin look like dark. But of course, when you go into that machine, you should also apply like sun lotion to avoid like damaging your skin. Okay, yeah. I mean, so I'm not saying like in the winter time nobody will buy sunscreen lotion. It's just like a number of people who buy the sunscreen lotion obviously is much smaller, right? This is understandable. Okay, so this type of goods has seasonality. This is what the seasonality means. Okay, so how do we avoid, remove this seasonality? Okay, we can use the technique called the differencing. Okay, we basically just obtain the difference between the value at each time step and the value 1 year earlier. Okay, we use that different value as our data set. Okay, I mean, yeah, summertime is sales better, but last year also summer sales better, right? So the large number minus large number, the difference will still be reasonably small, right? So if you do this differencing, use this differencing technique, then you are able to remove that seasonality, and then you do a prediction, okay, by using your model. And once you finish the prediction, you can add the seasonality back. You can add the seasonal pattern back to get the final predictions. Okay, so get rid of the trend or seasonality, okay, and do a prediction, and then add the trend and seasonality back. Okay, this type of thing, okay, is very important for like weighted moving average model or like ARIMA. Okay, this type of statistical approach. It is actually also, I mean, if you use RNN, it's not that necessary to use this, but it may also improve performance in some cases because the model will not have to learn the trend or the seasonality. So the model learns, what should I say? Like it learns like you only need to learn smaller amount of information, right? So sometimes it can help your the prediction to be better, okay, to perform better. So this is like one thing you can consider. But I'm not saying like we are going to do that here because, well, for the data we just generated, I mean it's just a very simple two sine wave plus some random number. So really like it's difficult to say there are certain seasonality or trends. I mean, but you get an idea. Okay, if your application has trend or seasonality, I mean, it is a good idea to get rid of them. Then do a prediction. Okay, and then add them back, add the trend or seasonality back. Okay. So now it comes to the multi-layer okay. So it's quite common to stack multiple layers of cells. Okay. So as shown in the next figure, we call it a deep RNN, this one. Okay. So I mean in Keras, okay, in TF.Keras, okay, it's very simple. Just stack recurrent layers, just like this. Okay, we still use sequential API and Keras layers, simple RNN, and you can see that we also increase the number of neurons. The first layer we have 20 RNN neurons, and we set return sequence to be true because we want to output sequence because the next layer is also RNN. So the RNN layer will expect the sequence. Okay, the RNN layer expects sequence. So we have to set return sequence to be true. Okay, and then the next layer is also 20 neuron return sequence to be true. Okay, and then the last one, okay, it's a simple RNN with 1 neuron. Okay, it also expects the series, time series data, but because we didn't set return sequence to be true, so you only output the last number. You only output the last number. So, by the way, how many parameters are we talking about here? Each of these has 2 weights, right? The weight for the what should I say? Like the input and the weight for the feedback, right? So we have 40, around 40. Okay, another 40, and well, we probably need to add some like bias. Okay, and we have 3. So totally about like about 50, 60, something like that. So the reason to make it like this is just to make sure the number of parameters is roughly the same as the number of parameters in that linear model. Okay, the linear model is 51 parameter, right? This one, for this one, the number of parameters is roughly the same. Okay, it's well, I should say slightly more, but not by much. Not by much. Okay, so you can train the. So yeah, I mean I already explained that. So if you compile, fit, and evaluate this model, you'll find that it reaches an MSE of 0.003. So we managed to beat the linear model. Okay, so you say, oh, it's just better by 0.001. Okay, because the linear model is MSE is 0.004, right? So it's only good for like a 0.001. But in terms of percentage, it's significant because it's 25% better, right? It's 25% better. So it is considered, I mean, a much improved performance. Okay? But there are some stuff that we can improve on this model. Okay? Because the last layer, okay, we use a single unit because we want to forecast a univariate time series. And this means we must have a single output value per time step. Okay, so having a single unit means that the hidden state is just a single number. It means like if you really consider, remember like the example I show you, I told you, okay, you are going to, the last layer, okay, you are going to expand 50 time step, and only the last one will be, the output of the last one will be used to compare with the ground truth, right? So we will have like a gradient flow back and to do all this. But you know, if you don't have like the gradient to come back from here, I mean, and having the gradient to flow back all the way 50 steps, I mean, it doesn't make much sense. I mean, those like, you know, you really don't need to have use the time. You really don't need to use the simple RNN for the last layer. For the last layer. So what you can do is actually you can replace. You can replace where is it? Sorry, go too far. Yeah. You can replace the last layer by a dense layer. Just use like one neuron there, okay? And it has almost the same effect anyway, okay? But if this one is a dense layer, then, okay, you don't have to, because this one doesn't expect the sequence input. So this one on the previous layer doesn't need to set the return sequence to be true anymore. Okay? So you have this, you just change to the dense layer. And there's another benefit of this, okay? Because like in the previous model, because the last layer, we are using hypertension by default, right? But if you want to use a different activation function, then it is perhaps better to use dense layer, because in the dense layer, it is more easily to incorporate different activation function. This is especially the case if your predicted value is, for example, within certain range. Okay, for example, I mean, if it's positive, remember, if it's positive, we prefer to use, for example, ReLU, right? Okay, but I mean, in a previous example, I mean, in the previous model, okay, because the simple RN use hypertension by default, so you know, it's difficult. I mean, we have to change that activation function. So you know, if you use dense layer with one neuron, then it's easier for us to control that. Okay, so this is one additional benefit, and then you will find that this model, if you train it and they compile it, okay, first it converges faster, okay, because well, there are several reasons for that. First, the last layer doesn't need to go through the back propagation through time, right? The back propagation through time, you know, is require more resource to train than the dense layer, okay? And the second, because dense layer, I mean, as I said, like by default, dense layer activation function is ReLU. ReLU activation function is easier to converge than hypertension. So, I mean, because of these considerations, so you will find that this model converges faster and it performs just as well. Okay, it performs just as well. I mean, I think like performance is still like 0.003, something like that. So plus you could change the output activation function if you want. Okay. So far we only predict one. I mean, from the past 50 time step, we only predict one number, right? We predict next value, right? But what if you want to predict like several time step ahead? This is kind of like you know, the project number 3. Okay, you want to predict like PM 2.5, not just 1 hour, but like 6 hours in advance, right? So what do we do? Okay, you could, okay, remember, because we have like our model, the model that we just trained is able to predict 1 hour, right? So you can do something like that. We predict 1 hour and then move the input from the past 50 to past 49 plus the newly predicted one. And then we predict the next hour. Okay, we keep shifting and predict the next hour and so on. Okay, so this is doable. This is doable. Okay, of course. I mean, if you want to do that, I mean, you have to change like the data set. I mean, in order for you to do that. But yeah, this is doable. Okay, you just like apply this model multiple times to get like you know, several time step ahead. Actually, I mean, here we want to predict like this time step 10 step ahead. Okay, this is, you know, quite more difficult than the previous problem, because previous problem only require you to predict one time step ahead. Now we need to predict 10 time step ahead with the same amount of information. Okay, so what happens is that, as you might expect it, the prediction for the next step will usually be more accurate than the predictions for later time steps. Why? Because, you know, the prediction, the first time step prediction, okay, you have a smaller error, right? You have smaller error. But that small error, because you use it as like as input for the next time step, right? To predict the next time step. So the error actually add up. The error actually add up. So it's going to be something like this. The blue cross represent the real value, okay, for the next time step. But the red point represent the predicted value, okay, when you apply this model 10 times. And you can see that the error, accumulated. It becomes bigger and bigger for the, for the following time steps. So this is perhaps not necessarily a good approach. Not necessarily a good approach. Okay, so what do we do? Okay, I mean, if you wonder what this piece of code is, I mean, this piece of code is just like we also need to generate because we want to predict from the past 50 time step, we want to predict the next 10 time steps. So we have to generate 60. So this is we do the plus 10, not plus 1. The other part is pretty much the same. Okay, and also, okay, what is the performance? Okay, so the naive approach, okay, this is terrible. Okay, it gives an MSE of about 0.223. This MSE is calculated by the prediction you have for the next 10 time steps. So 0.223. But the linear model gives an MSE about 0.01188. So linear model is actually better, okay, much better than using the RNN to forecast one step at a time, okay, to do this 10 times, okay, and also much faster to train and run, okay. So so what do we do? Okay, so here, okay, well, what you can do is that you can train and run your RNN to predict actually 10 time step. Okay, so here you can see, okay, before doing that, of course, you have to prepare your training set so that the ground truth is not just one number but 10 numbers. Okay, so here in the model you can see here, okay, 20, and dense layer you output 10 numbers. Okay, so instead of just outputting one number, you output 10 numbers directly. This 10 number you try to fit the next 10 numbers, okay, from this time series. And if you do that, okay, after training this model, you can predict next 10 value at once, okay, and the result, okay, it works nicely. Okay, the MSE for next 10 time step is about 0.008. So this is pretty good, right? It obviously outperforms the linear model by a lot. Okay, that's much better than the linear model. But we can still do better. Okay, indeed, instead of training the model to forecast next 10 values only at the very last time step, we can train it to forecast next 10 values at each and every time step. Okay, so we can convert now. I mean, what we are doing here, okay, up to now, we are doing sequence to vector. Sequence to vector. But now, okay, the next one, what we can do is we can actually convert this model into sequence to sequence. In other words, originally, the model we were using is this one. But now we can convert it to like this. Okay, but well, I think I'm out of time. Okay, we will talk about this next week. Okay, we'll talk about this out next week. I think we will finish this chapter next week, and then be able to advance. Not sure if we can advance to the next chapter, but at least before the end of this semester, I expect we finish the autoencoder part. okay, of the next set of slide. Okay, so any question? If no question, lecture. Okay, so we will finish this chapter and then hopefully like talk a little bit about the representation learning. Okay, and next lecture we are going to talk about the autoencoder. Okay, that's about it for this semester. Okay. So the week after next is going to be the final exam. Okay, and one thing to tell you guys is that, okay, the department actually has an announcement to make. Okay, because they want to reach as many vocational students as possible, and it took. This is not for you guys. Okay, it's for night class. Okay, for night session. So never mind. Okay, but okay. So the week after next is going to be the final exam, and then the third lecture. Okay, from today is going to be the project presentation. Okay, for the final term project, and for that day, okay, the TA is going to randomly decide an order. Okay, for your presentation. Okay, so the TA will announce like the order a week, at least a week prior to that day. Okay, and each presentation is going to take like maybe, because like in the afternoon session it's going to be quite a few groups. So we will see like each presentation. I mean, it's going to be maybe between 10 to 15 minutes, depending on how much I mean, we will decide about the length of the presentation, okay, and announce that maybe through the class, and during that day, okay, we will provide like a pizza, okay, for you guys, okay, as usual, okay. So you guys are more than welcome to come a little bit early, like around 12:30, okay, to enjoy the pizza, okay, before your presentation, okay. And some students asked me about the final exam. I mean, is it okay to bring like the one-page cheat sheet? Okay. Yes. Okay. You guys are allowed to bring one-page A4. Okay. Cheat sheet. Okay. Whatever you wrote on that page. Okay. I don't care. Okay. But it's not going to be a whole book. Okay, just one page. Okay, and I think like everything remains like remains the same. Like just like what we how I told this class last time. Okay, so hopefully like you guys have a better understanding. And already, by the way, I already have the sample final uploaded to the EE class. Okay, so just in case if you don't know the format of the final exam, please go check it out. Okay, we normally provide like a little bit more questions than required. Okay, so that you can have a little bit of wiggling room. Okay. Like you can drop like one or two questions, like
I mean, in your final exam, okay, hopefully, I mean, this is going to help you to get a better grade, okay? So, okay, so back to our lecture, okay? So last time we talked about the RNN, right? And we actually create a model that is used to predict like the time series data, okay? Originally, we want to create, we want to predict like just one time step, okay? But later on, we say, okay, now we want to predict like 10 time steps, okay? Then, okay, we found that if you apply like the model that predict like the next time step 10 times for those 10, additional time steps, it's going to, the performance is going to be very poor because like the error actually gets accumulated. So what we can do is that we can convert, we change the model so that it predict like the next 10 time step like together, okay, just in one prediction. This way you avoid like the issue of like error accumulation, okay. So yes, so the performance, okay, if you use that this model, yes, it's going to perform much better than using like the original model to do like a prediction 10 times. Okay, but actually, okay, you can even you can actually like convert, because the previous models that we talked about, okay, they are all like sequence to vector models. Okay, so we can actually convert this sequence, our sequence to vector model into sequence to sequence model. So what is the difference? Okay, in the sequence to sequence model is something like this. Okay, yeah. Instead of training the model to forecast the next 10 values only at the very last time step, okay, we actually, in the sequence to sequence, we train it to forecast the next 10 values at each and every time step. So it's going to be something like that. Okay, you get the first 10 steps, first 10 values, and use that to predict the next 10 values. And then, okay, you move one step ahead. Okay, so say like, okay, say this is like, okay, so this is the first 10. So you are going to, your model is going to use this first 10 values to predict the next 10 values. Okay? And then, okay, your model is going to move one step, okay? So the next is going to be something like this. From the second element to the 11th, okay? So this is going to be the next sequence, okay? And then, well, the second next 10 element. And you use that to predict like, from here to one more element, okay, something like that. Okay, so you predict this, you use this to predict this one. And then you move one step and you predict next 10 and so on. Okay, so that's the idea, okay? So basically, okay, the advantage of this technique, okay, the loss will contain a term for the output of the RNN at each and every time step. Because now, okay, originally you use the whole sequence, and then you only account for the last output, the loss, okay, only accounts for the last output, okay? But now, because, okay, for every, like, for example, from here, you predict the next time step, and you can use this to compare with the ground truth, well, for the loss, and you can use that, I mean, to fix, I mean, to get the gradient to fix your model, okay, to improve your model. So you get a lot of error gradient, okay, compared with the original approach, okay. So yeah, so because you get a lot of gradient, I mean, in flowing through the model, so this gradient will both stabilize and speed up training. So what do we do? Okay, the first thing we need to do, obviously, is to prepare our data so that, like, we take the first 10 and then predict the next 10 and so on. Okay, but actually, what we do is, you know, not exactly like this. We are going to create what we call a causal model. Okay, so it's not like you use first 10 to predict the next 10. We are going to use the first 10 to predict, to predict like this from first 10. This is the first 10. Okay, and then we want to predict here, from here to from the second element to the 11th. So there's we only predict like one additional element in this round. Okay, and then we move up from the second element to the 11th. We predict like the third one to the third one to the 12th element. So every round we only predict one more. Okay, and the reason this is called the causal model is because like you can see, you know, in this case, okay, because you use the first 10 elements, and you predict like from the second element to the last one plus a new element. So some part of the input somehow overlap with the output, right? So that is why this is called the causal model. There's overlap between your X trend and Y trend. X trend is your input. Y trend is your ground truth. Okay. So what you need to do is here. Okay. You need to prepare your data accordingly. Okay. You have your X trend ready and you have your Y trend ready. Okay. And then after that, okay, you also need to change the model. Okay. Remember, now it's a sequence to sequence, right? So your input obviously is still, I mean, it's a set. It's just a sequence. Okay. But the output is going to be a sequence. So remember, like originally, okay, these two lines remains the same. Okay, we have like a simple RNN. Okay, return sequence equal to true. Okay, and this part is the same. However, here, okay, originally we used like just the dense layer with 10 elements, right? With 10 neurons. But now, okay, because we want to convert it into the sequence, so we can wrap this layer by the time distributed, okay, so that we make the last make the output a sequence as well, okay. So this time distributed is going to convert the output into the shape of the sequence, okay. So, supposing if you use the dense layer and and train it using like the sequence to sequence. I mean, it's supposed to work as well, okay? But the reason to add the time distributed dense, okay, to wrap this dense layer with the time distributed is to make it more verbose that you want this output to be sequenced, which is normally a better practice because because dense can be used for either like the vector output or sequence output. But if you don't wrap it with the time distributed, we don't know what type of model we are doing here. So it is a better idea to make it more verbose, okay? Make it like obvious. Okay, here we are dealing with a sequence to sequence model. Okay, and then there's one small tiny detail that we do need to be careful. Okay, we train it like everything looks just right, but there's one thing. Okay, because now remember, every time we use this 10, the first 10, and we predict the next. Well, the window that shift like one element. We predict that, and then and so on. So, but yes, this is going to be used for training, but for evaluation, when it comes to evaluating the model, the only thing that matters is because eventually, say we have like the first 50 elements. Obviously, with this shifting, you are able to do this many times. But the thing that really matters is this next 10 values. This next 10 values. We want to see the error, how much error this last 10, the future 10, or I should say like the 51st to the 60th elements. That you predicted, like how far away they are from the ground truth. This is what we really care, right? The previous, value, we will use that for training, but we are not going to use that for evaluation. But during evaluation, what matters is the accuracy of the 51st to 60th. Element. So you should define a separate MSE that care only for the last time step. Okay. So you define this. Okay. This return Keras matrix, mean square error. Okay, the last one. Okay, and then once you define this last time step MSE, you can have your optimizer. Okay, we use Adam here, and then we compile our model, which use the loss function MSE, optimizer. Okay, metric, optimizer is the Adam. Okay, the matrix is last time step MSE. Okay, so these two are different. This one is to measure the performance of the model. This one is used during training. Okay? You need to be very careful to understand the difference between these two. Okay? So if you use this and train this model, the MSE you get is about 0.006. Okay? The previous one gives you the MSE of 0.008. So this one is 25% better than the previous model. The previous model is the sequence to vector. This one, sequence to sequence, give you even lower MSE. So this is a better approach. Okay, 25% improvement is not is significant. Okay, So obviously you can combine this approach with the first one. What do I mean? Okay. For example, say you want to predict like the long-term time series. Say like okay, use the first 50 time steps to predict next 50 time steps. Then what you do is that okay, you use this one to predict the next 10 value, and then use this sequence to predict the next 10 time value and so on. So you can apply this thing 5 times to predict like the next 50 values. So sort of like combining the first approach and the second approach. So obviously, I mean, when you do that too much, okay, you still get like error accumulation, right? So you know, when you should weigh weighing how many additional sequence you want to predict. I mean, each time. Okay. So for example, okay, if you use like the first 50 to predict the next 10, okay, that's reasonable, right? That's reasonable, okay, because you should have enough information to predict the next 10. But let me use a very, extreme example. Okay, say you have the first 50 value, and you want to predict like the sequence of the next 100 sequence. Then, okay, you can use the first 50 to predict next 10, and do it 10 times, right? Okay, so that's what we meant by combining these two approaches. Okay, then I mean, because each time you get the 10 additional value, and then you do it 10 times, you get the next 100 values. Okay, but if you say, oh, I don't like error accumulation, let's do it in one prediction. So you use the first 50 to predict next 100 in one try. Probably that's not going to perform very well. Why? Think about that. You don't have a lot of information to predict this long, right? In one prediction. Okay, so this is like a trade-off here. Okay, I mean obviously if you have a long sequence and you predict like a shorter sequence, it will give you a much accurate prediction, and then you can tap on that more accurate model. I mean several times. Okay, to form a longer prediction. Yes, but on the other hand, okay, if you use a shorter sequence and you expect to predict like one long sequence in just using, you want to train a model to do that. That model, most likely will not perform very well. Okay, it's just because you don't have enough information. Okay, so this is like which these two approaches, yeah, they can be combined. As for like how do you combine them? That's something you can think about. Actually, for the project 3, okay, you are required to predict like the next 6 hours, PM 2.5, right? So say, if you just use the previous 3 hours to predict next 6 hours, well, most likely it's not going to perform very well. Okay, just want to give you an idea. You probably want to use a much longer sequence to do the prediction in order to make it like the next 6 hours prediction better. Okay? So also, okay, when you forecast a series, okay, it is useful to have some error estimation, okay, for your prediction, okay, like how accurate or how bad your prediction is, okay. So for this purpose, okay, the MC dropout is a good technique to apply. Okay, we talk about MC dropout in chapter 11. Okay, 2 chapters, ago. Okay, so basically you can add MC dropout layer. Okay, with each memory cell, and this will help you, to estimate what we call error bar, or like the variance, okay, of your prediction. So which will you get a mean and standard deviation, okay, which will help you to determine, okay, if your prediction is trustworthy or not. Okay, this is important. For many time series forecasts. For example, like if you want to predict like the stock market trend, okay, because you are investing money on it, right? So obviously you want to make sure, okay, your prediction is accurate enough, okay, so that your money you invested is not going to be a waste, okay. So, okay, at this point, okay, we finished like a lot of discussion but as I mentioned at the beginning of this chapter, okay, there are, the island has some issues that we need to deal with, okay. Yeah. So, for example, when it comes to predicting the forecasting time series or handling other kind of sequence, RNN, is used for that purpose, but they do not perform well on long time series or sequence. Why? Okay. So first, to train on long sequence, okay, we must run it over many time steps, making the unrolled RN through time a very deep network. Here, when we say deep network, I'm talking about here. Okay, we need to, unroll many steps. Okay, so when I say it's going to be a deep network, I'm not talking about the depth here. I'm talking about the depth horizontally. Okay, because you are going to expand your island through many time steps. Okay, which will create some issue. Okay, because the depth is not there are two depths that we are discussing here. The one of depth is the number of layers, which is the same as like as we discussed for the other networks such as CNN or MLP. But the other depth, this unrolled through time. Okay, this is especially, the case for long sequence. Okay, and this type of thing, okay, only is this issue only happens in RNN. Okay, you don't have that in CNN, you don't have that in MLP. Okay, so I just want you to be aware. Okay, why training a long sequence? Okay, you encounter issue. We need to explain, we need to discuss, here, different. Where is it? Okay. Okay. So these are, okay. When it gets deeper, okay, even though we are talking about, the other dimension, deep in other dimension. Okay, yeah, the network okay, the training of the network may suffer from unstable gradient problem. Okay, so it may take forever to train, or training may be unstable. Okay, another issue, okay, when an RNN processes a long sequence, it will gradually forget, what we did at an earlier sequence. Okay, so the first input in the sequence, it will gradually be lost. Okay, especially during the unroll through time process. So what do we do? Okay, so let's talk about these two problems. Okay, two issues. How do we solve them? Okay, the first issue. Okay, unstable gradient problem. Okay, yeah, we talk about many ways to deal with that. Especially in chapter 11. Okay, so for example, like good parameter initialization. Remember the He initialization or Glorot initialization. All those parameter initialization or faster optimizers. We talk about Adam. We talk about Nathan. All those optimizers. Or dropout. Okay, this okay, this actually still helps. They are still useful. They are still useful. Okay. However, okay, one thing is slightly different. Non-saturating activation functions such as reloop, okay, may not help as much here. Okay. Why is that? Okay. They may actually lead the RNN to be even more unstable during training. Okay, because when you are doing gradient descent update, okay, the weights in the way that increase the output slightly at the first time step. Okay, well, here. When you're doing the gradient update, okay, keep in mind, okay, this training, okay, for one iteration, okay, this expansion or like unroll through time, it's just one iteration, right? So this gradient flow back. Okay, even though I show you, okay, they look like okay, you have this and this and this and this. They are different model, right? They looks like a different model, but they actually all this represent the same thing, right? All this represent the same thing. So when you are calculating the gradient, yeah, you are calculating the gradient for this, but actually this and this, they actually share the same weight because they actually are the same thing, right? Even though we are unrolled through time, but they represent the same stuff here. So they use the same weight. All these weights are the same, and this during one iteration. So if your activation function result in slightly larger result, then those larger result, because you are using the exactly same weight, that slightly increased result is going to be enlarged and enlarged to a point that it explodes. Okay? So because this unroll through time is special in our, as I said, this is not going to, we don't have that in CNN, we don't have that in MLP. So in the MLP, okay, when you train a layer, say, if you, of course, CNN or MLP, it's going to be like, we don't have unroll through time. So actually, when you train a layer, okay, something like this, of course, they represent different weights, right? Each layer has different weights. But now, okay, all these have the same weight. So that's the primary difference. Okay, the primary difference. So, okay, the same weights are used at every time step. Okay, so the output at the second time step may also be slightly increased, and so and the third step, and so third time step, and so on. So eventually, okay, the output until the output explodes. Okay, so so because when we say non-saturated, I'm talking about. I mean, you know reloads like this, right? Right? So you, I mean, this value can go very big, right? This value can go very big. The result of the reload activation function can be very big, right? After you apply reload, I mean, it could be very big. But on the other hand, the saturated activation function, okay, such as hypertension, okay, the value is the result is in between -1 to +1, right? Okay, so it is bounded, right? Yeah, we have the saturating function. The issue is like the gradient is going to be very small. Yeah, we have that issue as well, but at least like the output is not going to be, like unbounded. Okay, so the saturating function, such as like hypertension, okay, does not have that issue, does not have that risk. Okay, so that is why, okay, the hypertension in the RNN is normally used as the default, Okay, I'm not saying reload can never be used, but I'm just saying, I mean, in RNN, reload is not as popular as hypertension. Okay, not as popular. Of course, you can say, oh, I mean, how about gradient? Because saturation function have that vanishing gradient issue, right? But as I said, like in other, most of the issue comes. I mean, when we say in the other, the unstable gradient, I mean, what the unstable gradient in other actually normally refer to exploding gradient, because like so it's somehow like I mean, especially in long sequence training, okay, I mean, either gradient or like the result function gets enlarged and enlarged, okay, eventually explode, okay, but yeah, I mean, yeah, for saturating function, I mean, if you have that vanishing gradient problem, we already know a lot of technique to fight with that. We already know a lot of techniques, okay, especially the ones that we learned from the chapter 11. I mean, they are still okay. Okay, another way, okay, yeah, the gradient themselves can explode too. Okay, so if you notice that training is unstable, most of the case is because of the exploding gradient. Okay. So you may want to monitor the size of the gradient, okay? And how do we monitor the size of gradient? I mean, we talk about TensorBoard, right? TensorBoard is able to allows you to monitor the gradient, like during training, okay? And if that happens, you can also use gradient clipping. We talk about gradient clipping in chapter 11, right? Okay, which help you to prevent gradient, exploding gradient as well. Okay. So, yeah, and remember, like in chapter 11, I mentioned like batch normalization is important technique, right? I mean, this is so important that in chapter 12, I mean, when we talk about CMN I mean, you see batch normalization, I mean, always used like right after the convolutional layer. Okay. Yeah, I mean, how about in RNN? Yes, we can still use batch normalization, but you know, there's some research that you know, they found out that BN was slightly beneficial only when it was applied to the input, not to the hidden layer, hidden state. Okay, so because if you try to apply batch normalization directly, then it will apply to both the input and the hidden state, because hidden state is also considered, I mean, that's the feedback, remember? I mean, that's also considered as the input of the neuron, okay? So in other words, okay, you know, it's slightly better than nothing when applied between recurrent layers, okay? Well, but not within recurrent layer, okay? So, so basically, okay, in Keras, okay, this can be done by adding a batch normalization layer before each recurrent layer. But the issue is, yeah, I mean, the batch normalization, you cannot expect the BM help you a lot. It's not like convolutional neural network or I mean, you know, the other cases like BM help a lot. Okay, I mean, instead, if you say batch normalization doesn't help that much, what else? What other option do we have? Okay, there's a concept called layer normalization. Okay, which was proposed in a 2016 paper. Okay, this concept, I'm sorry, is similar to batch normalization, but instead of normalizing across batch dimension, it normalizes across feature dimension. Okay, so it normalizes your features. Okay, I mean based on different features. Okay, so the advantage of this is that it can compute the required statistics on the fly at each time step. So you don't need to remember in the batch normalization. If you still remember our discussion, in chapter 11, you will know that batch normalization during training and during inference act differently. Remember? Because during training, you have the batch, right? So you get those statistics from each batch easily. But during inference, because you may not have that batch concept, right? So you actually have to, estimate those statistics, okay, from during the mini batch, from the mini batch, training, process, okay, and use that in the inference. But the layer normalization, okay, it remains the same, okay, regardless it's you are doing training or you are doing inference, okay, so it's a much easier, process, okay. So normalization will learn, scale, and offset parameter for each input, okay, directly. And in RNN, it is typically used right after linear combination and before and the hidden state, and before the activation function is applied. So, we can implement layer normalization in Keras, okay, with a simple memory cell, okay. So this is an example, okay. Class layer normalization simple RNN cell. Okay, it is a subclass, the layer. Okay, and here, okay, these are, I mean, pretty much, very very easy. Okay, so we don't need to change that much. The only thing we add is here. We create this star layers, layer normalization. Okay, but remember, I mean, we don't specify their relationship. Like in here, we specify their relation actually in the call method. So here, okay, you can see that, okay, we first compute the output, okay, first, and then, okay, we apply the layer normalization to this output. Okay, oh, by the way, the output and new states, I mean, they are the same. I mean, because it's a simple RNN cell. We know that, right? And the output and the state are the same. So then we apply the layer normalization first before we apply the activation function. Okay? And then we just output the same thing twice. The first one is used as an output. The second one is used as a state. The state is actually a list because, I mean, you know, in general, I mean, the RNN cell can have more than one state. Okay, so that is why maybe it is like a list instead of just one value. Okay? So, yeah, I think I already explained like what this code is. So, yeah, not much to explain here. And then you can use this LN simple RNN cell to create a model like this. Model, okay, still use sequential API. So in the layers RNN, okay, you use the LNS simple RNN cell, okay, to create like 20 this. No, not. Yeah, this is a simple RNN cell. Yeah, this is simple RNN cell, and we use that to create. To create a simple RNN cell with the layer normalization. Okay, we have 20 simple RNN cell with the layer normalization, and the other parts remains the same. Okay, we apply this LN simple RNN cell. Okay, and the other part. So up to now, okay, this is like one technique you could use, okay, to improve the training and the fight with the exploding gradient in RNN. Okay, so let's take 10 minutes break. When we come back, we will continue our discussion on the other technique that help you to train RNN. Like just a few minutes ago, right? So if you think about that, if Dory is doing translation of a long sentence, by the time she finished reading that sentence, okay, she already forgot the beginning of the sentence. But obviously the translation, okay, of a sentence, okay, the whole sentence is important in the translation, right? We talk about that. I mean, the whole sentence, not only the beginning, but also the end of the sentence. I mean, is basically, important. For the translation. So if you finish the sentence and you forget the beginning of the sentence, of course you are not able to do this translation well. Okay. So what do we do? Okay. There are several types of cells, okay, with long-term memory, okay, that have been introduced, okay, and these long-term memory cells they are so successful that nowadays, nobody use basic RN cell anymore. Okay, so the first type is, that is the most commonly used one. Is called LSTM, LSTM cell. Okay, what is LSTM? LSTM stands for long short-term memory. Long short-term memory cell. Okay, abbreviated as LSTM. So this actually was proposed in 1997. So think about this. This 1997, that was a long, long time ago. Okay, 25 years ago. Okay, but at that time, when it was proposed, at the beginning, it is years by many, many researchers. Okay, so if you consider LSTM cell as a black box, so you just use it. Okay, you can use it just like a basic RNN cell, but you are going to get a lot of benefits, such as like you will perform better, training will converge faster, you will detect long-term dependencies in the data. So you see all these benefits. Okay, the only thing you need is to, here. You just change this into keras.layers.lstm. All the other part remains the same. Okay, and this is already going to make your model perform better. Okay, especially for long sequence. Okay, this model will learn much better. The pattern, the long sequence. So another way to use the LSTM cells, you just use the genetic keras.layers.rnn, but inside like parentheses, you specify you want to use LSTM cell. You specify how many cells you want. Okay, so the other parts remains the same. But if you ask me which one, this version or this version, okay, which version is better? Okay, I will tell you to use this version. Why? Because in this version, okay, this LSTM layer, okay, has been optimized, okay, for GPU. So in general, okay, it is preferred to use this one instead of this one. Okay, but that's just like in terms of the speed. Okay, the speed. But what is the LSTM cell? How does it work internally? Okay, you can see this is the internal architecture of an LSTM cell. Okay, and you can see this FC stands for fully connected. Okay, fully connected layer. Okay, and so you have like the input that goes here. Then the input is fed to all these 4 places, and the previous time, the state of the previous time step is also fed into all these 4 rocks. Okay, and you can see that actually we have this C T-1 and H T-1. These 2 are both states. Okay, these 2 are both states. So remember I told you, okay, the state is a list. Okay, some RN cell has multiple states. So LSTM cell has, for example, in this case, 2 states. Okay, so you may ask, what are the purposes of these 2 different states? Okay, let me put it this way. Okay, C stands for long-term state. H stands for the shortened state. Okay? And you see, this long-term state, okay, after it enters the LSTM cell, first we have this. This is like okay. If you see this basically just means this one is like logistic function, right? Logistic function. So when you see this one, it's just like the other two, like here. Okay, they act as gates. They are gates. Okay, so this one is always called forget gate. Forget gate. So this gate pretty much control, okay, what part in the long-term state to forget. Okay, what part in the long-term state to forget. And then, okay, and then this forget gate, this forget gate obviously is controlled by the shortened state as well as the input. Okay, and also from the shortened state and the input, okay, this GT, okay, is used to determine which part in the input is more important to be kept long term. Okay, so this part control which part of the input is more important to be kept for long term. Okay, so this part of information, or remember, this is like hypertension. Okay, this is hypertension. So it's just like a regular neural network. Okay, here we just use this hypertension to free content layer to filter like the important information. Okay, to be kept long term. So this information is is going to here, and then we have this one. Okay, we call this input gate. So this input gate is once again controlled by the shortened state and the input. Okay, again we use this to determine like okay, this input. Okay, which part is more important? Okay, and then okay, this important part